Right, okay, in that case, I will introduce our speaker. So it's a great pleasure to have Jan Schneider of the Ecole Polytechnique with us today. Jan did his master's at Heidelberg with Philip Haug, and he worked on lattice gauge theories. And since then, he's been a PhD student with Laurent Sanchez Palencia at the Ecole Polytechnique, working on a variety of tensor network projects. He's worked on correlation and information spreading in spin chains. And today he's going to be telling us about some interesting entanglement measures in long-range spin chains. So with that, over to you, Jan. The floor is yours.
Yes, hello. So welcome, everybody. Thank you for attending my talk. I want to tell you about our recent project that we put out on the archive together with Stephen, in fact. It's about the entanglement spectrum and the quantum phase diagram of the long-range XXZ chain. And to begin with, I would just like to emphasize the central role that entanglement plays in condensed matter physics, or has taken up in recent years. So one of the most celebrated results is, of course, the area law of entanglement of ground states of gapped Hamiltonians. Otherwise, there are sub-leading terms to this entanglement entropy, which have been successfully used to characterize symmetry breaking, topological order, or quantum phase transitions. And moreover, disordered systems and many-body localization has been revisited with tools through the lens of quantum entanglement. And going beyond just a simple entropy, the entanglement spectrum has been shown to host the excitation spectrum of the topological edge modes of topologically ordered matter. This is typically called the Lee and Haldane conjecture. And ever since Lee and Haldane put out their seminal work about 12 years ago, it has sparked a lot of interest in this observable of the entanglement spectrum, which leads me to the following statement that the entanglement spectrum has been shown to signal phase transitions in spin chains in the singular behavior of the Schmidt gap or in degeneracy lifts of its spectral lines. And with the Schmidt gap, I mean the difference between the lowest entanglement line and the next one. So with that, I would like to pose our objective for today. We want to understand the phase diagram of the long-range XXZ model. There are two parameters in our model. So first, delta, and the other one would be alpha. So that we're going to understand the phase diagram in the delta alpha plane. Okay, so next, let's just have a look at this bracket here. We can see a spin-spin interaction between two spins at side r and r prime in the x direction, in the y direction, and with an anisotropic coupling in the z direction. Furthermore, there's an all-to-all connection, so all spins are talking to each other. However, the amplitude of the coupling strength falls off with the power law determined by alpha. Yes. So why do we do this? First of all, it's experimentally relevant. So quantum stimulated devices can realize this very much, this Hamiltonian. So let's have a look. Secondly, there are, from a theoretical side, there are a few ingredients in the short range system that make this all a bit very interesting and very interesting test bed. First of all, we know that this system in the short range case is integrable with the beta ansatz. There are three phases. There's an antiferromagnetic phase for the choice of our variables delta smaller than -1.
Just to be clear, this is the spin half case, right?
Yes, sorry, yes. So these are spin 1/2 operators. Yes, yes, exactly. Okay, so antiferromagnetic phase for delta smaller than -1, paramagnetic for a delta between -1 and +1. We're also going to call it XY phase. And the ferromagnetic phase for delta larger than 1. Okay, there's a first order phase transition between the XY and ferromagnetic phase. And there's an infinite order phase transition between the antiferromagnetic and XY phase at delta -1. And thirdly, there's a conformal field theory description of this XY phase. The tool is called Luttinger liquid theory. it has conformal field theory with central charge 1, but these are details we're going to talk about later. Third and last but not least, I want to say that this model, the XXZ model, is one of the most archetypical spin models. It has been studied in various contexts, and so let's take this as our test bed for understanding more entanglement properties in the spin chain. Okay. Furthermore, I would like to emphasize that this lattice model and the categories of lattice models that we, or specifically I, am interested in are one-dimensional. They have long-range interactions, right? So they're the constituents talk to each other over a long distance. They're non-relativistic, and they're relevant for experimental setups that can be realized with artificial ion crystals in optical lattices, with Rydberg gases, or generally in other systems where where the Coulomb interaction of the constituents is not completely screened. And here, just as a little illustration, there are two illustrations from two papers that show you that, okay, this is really an experimental setup. Here we have spin atoms in an optical trap illustrated by this bent curve. Laser light interactions can engineer this long range interaction. The intensity falls off with the power law. We can engineer a total magnetic field, etc. The same is true in this experimental setup, where the arrows here represent the laser light pumping these atoms into these ions into a specific state, and then engineering, for example, in this case, the XY Hamiltonian. All right. So next, I would like to talk about the methods that we've been using. The most prominent of them being the density matrix renormalization group, to find the ground state or the dominating eigenvector of a many-body Hamiltonian operator. And secondly, technical detail, we're going to use the iTensor library written in Julia, where we're going to model the long-range interaction as a sum of exponentially decaying interactions. Because these exponentially decaying interactions are very easy to implement. This is a technical detail. Okay. The next thing that I need to talk about is the Schmidt decomposition and what this means for our numerics, and how we can use this to obtain the entanglement spectrum. So first off, I would like to emphasize that equation number 2 and 3 are supposed to represent the same thing. So if you're familiar with what is called a Schmidt decomposition, you've probably seen this equation. And if you have never seen how a matrix product state is usually visualized, excusing myself, we can talk about this later. I expect backup. I would just say, okay, this here, these little A's, they are tensors. The number of legs that come out of them represents their rank. If we connect two legs of two tensors, we represent a tensor contraction. And hence, this is a product of matrices, or otherwise a matrix product state. And this equation represents the Schmidt decomposition. So let's talk about it in a little bit more detail. We can take any given state in a Hilbert space and write it as a linear superposition of the many-body bases. However, at the same time, and this is a fundamental theorem of linear algebra, we can write it as a decomposition in two bases, which live in two different subspaces of the Hilbert space. I'm going to call them A and B, these two subspaces. And they have coefficients of lambda L in front of them. So this decomposition has coefficients lambda L. We are going to call them Schmidt values. And as a graphical representation, we can think of this as the singular value decomposition. We're going to use the singular value decomposition, another fundamental theorem of linear algebra, which decomposes any matrix M into the product of three matrices, whereas the matrix S here is diagonal. U is right orthogonal. That means U dagger U is 1. And V dagger here is left orthogonal, meaning that V dagger V is equal to 1. Okay, so if we're going to throw our singular value decomposition onto this matrix product state, on the one hand from the right and the other hand from the left, we're going to meet somewhere in the middle, where this diagonal matrix is sort of the remainder. This gives us the orthogonal basis in orthonormal basis in the subspace A, very visually here with these remaining U matrices. And on the other hand, we have the basis in B given by these V dagger matrices, and in the middle there's this entanglement building up represented in these coefficients lambda L. And to make this more explicit, we can define the entanglement spectrum or from the eigenvalues of the reduced density matrix or row A. So we're going to obtain this by tracing out overall basis states in the complement subsystem B of the complete reduced of the complete density matrix, which is nothing but the absolute value square of the Schmidt coefficients and then a diagonal basis. Okay, and in the following, we're going to map these values, lambda L absolute value squared, with minus the logarithm on values that we're going to call psi L. And these are going to be named entanglement energies, simply because these here are values between 1 and 0, which are going to be mapped with minus the logarithm on values that are between 0 and infinity. There is a more fundamental understanding of why these are called energies. There is a Hamiltonian operator that has these values as a spectrum. But for now, let's keep it like this. We can talk about this later if you would like to. Okay, so this is the entanglement spectrum that we're going to talk about later. Another tool that we're going to use is the geometric entanglement. So why do we use it? First of all, because the AFM, the antiferromagnetic XY phase transition, is of infinite order, which means that there's no local measurement which shows this phase transition, which has a signal in this phase transition. So what people have already used is geometric entanglement to highlight this phase transition. So let's define it. The geometric entanglement is defined as the logarithm to the base of 2 of the overlap of the state, here psi as a state, with another state that is defined to be, that is set to be a product state, and then its absolute value square. So what does this do? First of all, the absolute value square of a state with any other state defines something like, it defines a metric in the Hilbert space, which then gives us a distance, right? So this is the metric in Hilbert space, and the two states absolute value squared overlap means the distance between them geometrically. We're going to take the maximum overlap, which means the minimal distance. Okay, and then from this minimal distance, we take the logarithm, because we assume this distance to be extensive. So we take the logarithm and divide system size out to get something that is hopefully well defined in the infinite volume limit. Okay, so now let's quickly talk about what product states are in terms of matrix product states. They're very easily to be understood. They're a product of matrices, whereas the dimension of this link between two matrices is equal to 1. It's everywhere equal to the unity. Okay, yeah. So these are in fact single numbers. They're not very large matrices, and because their dimension is precisely 1. And I would like to emphasize that I'm not the first one to to use this geometric entanglement. Indeed, Victor Oros used it to show the phase transition, and John Gould, as well as, if I'm correctly aware, somebody in the audience already showed its usefulness in the Heisenberg model, in the two-dimensional Heisenberg model. Yes, so let's have a look at how we can actually measure this. Very briefly, we're going to take our ground state of that we have just obtained from the density matrix renormalization group algorithm, from the DMRG algorithm. We truncate it to a unique singular value, to the largest one, and take this as an ansatz for an optimization sweep procedure, which means that, okay, let me first introduce you to this concept. If you've never seen a matrix product state, this is how an overlap of two states looks like. All matrices are, all open indices are contracted, which means that the result of this operation must be a complex or real number. Okay, that's good. That means it's an overlap. Secondly, in the bottom row here represents the ket of our ground state, and in the top row represents the ansatz of our of the truncation. So this top row is the truncation of exactly the same state, and then we're going to take this object, compute it, and maximize it with respect to varying these entries. And this is how we can in fact compute the geometric entanglement. Okay, so let's have a look. Let's dive into it. This is how it looks like. In the phase diagram of delta versus 1 over alpha. Okay, so first let me draw your attention to the line here at +1, delta +1. There's always a step from any finite value of the geometric entanglement to 0 value of geometric entanglement. Okay, as exemplary to just show you the one-dimensional curve, I've taken out here 3 cuts that represented in this color coding. So in blue, the short range case, which is represented here. I hope you can see my mouse, by the way. I'm not entirely sure if you can see my cursor where it is.
Yeah, we can.
Okay, perfect. So it doesn't, it makes sense when I'm pointing around here. Yes, so here you can see a step for all values of alpha. And this is rather trivial. So the long range interactions do not change the phase transition. It's to be expected. There is the state in the ferromagnetic phase is completely polarized, and the all-to-all connection from long range interactions doesn't change this completely polarization, and in fact enforces it stronger. Okay, next we can see in the short range case, the blue curve, very nicely the peak for the infinite order phase transition at delta -1. And then we can see for longer ranged interactions, this phase transition shifts to lower deltas, which are here marked by the maximum is always marked by this red dot. Okay, so this is our little phase diagram from this one observable. So let's continue with the next one.
Sorry, can you just
yes, please.
go back to the so which part of this phase diagram represents the conformal phase transition? Is that the line at delta =1, or?
Yes, so this phase here, XY phase, this is the one that can be described by a conformal field theory.
Mm-hmm.
So here's a phase transition away from this, and here's another phase transition away from this conformal field theory. As a matter of fact, there is another phase transition that is not highlighted by the geometric entanglement away from this conformal field theory. And I'm going to talk about it later. And it's going to be I hope it's going to be very interesting how we find this. but it's not signaled in the geometric entanglement. So there's one, you would expect one for large alpha. For an alpha that is going towards 0, there's an all-to-all connection, and mean field theory is entirely correct. And in fact, you would expect something like a continuous symmetry breaking phase, because Merman-Wagner theorem does not apply anymore. Like formally, it does not hold for long-range interactions, and at some point, you expect it to be explicitly broken. And we don't. Yeah.
You said that this is an infinite order phase transition.
Yes.
So would this be like the KT transition?
Sorry, a BKT.
Yes.
Yes, I think people typically call it BKT type. However, there's no topology, like this is one dimension, so it's topology for poor people. Yeah.
So like usually the BKT transition, this is associated with the presence of vortices.
Yes.
So in your case, is there something like that?
Not that I'm aware of. I don't know anything that that builds up like a vortex in this one-dimensional case. Why is it called infinite order? Because the beta ansatz allows us to, in the short-range case, the beta ansatz allows us to construct a few observables. For example, the energy or another thermodynamic state function. And it's differentiable. It's analytic at that point. The function itself is analytic, which means that we can differentiate it infinitely many times and do not find the phase transition. Like there's no signal in this, in the free energy, neither in the two-point function. Again, the two-point function is infinitely many times differentiable. It's analytic. I think that's the origin of the name, like the real origin why it's called infinite order phase transition.
Thanks.
Yeah. Further questions to this plot? Okay, so let me continue with the entanglement spectrum. So this is our next observable. Let's talk about it piece by piece. Let's start again. Oh, sorry, I cannot move over the animation. In fact, it's an animation. It's a bit sad. I cannot move over it and point at things. So let me try to explain where I would like to draw your attention at delta is equal to +1. You can see, so first of all, x-axis is delta, y-axis is the entanglement energy, is this exact, the different Schmidt values. Mapped with minus the logarithm to numbers between 0 and plus infinity. Okay, the first is obviously blue, the second is orange, green, etc. pp. Let's focus on delta +1. There you can see a single entanglement energy, and all the other ones are diverging. Okay, this is nice. This is exactly what I've just been saying. There is a phase transition signaled in the diverging difference between the first one and the next one. Furthermore, the value of this entanglement energy is 0, which means that the Schmidt value was 1, so minus the logarithm is 0. And all the other ones are diverging, which means that the Schmidt values were 0. Okay, this entirely describes perfectly that this state, this ground state at this delta is a product state. Yeah, all other Schmidt values diverge to infinity. All other entanglement energies diverge to infinity, and there's a single entanglement energy left. Okay, the same is sort of happening for delta to minus infinity. Yeah, you can. I hope you believe me here that you can see the sort of slow divergence of the entanglement energies for delta to minus infinity. Yeah, except for the first one. Okay, this is also something.
One question, just for quick clarification. I think I missed it. So these different colors are the exponentials of the different Schmidt values.
Yes.
Why do you have like sub n of them, you truncating it, like you take
Yeah,
only the structural artists?
Yeah, I have, I don't know, I have 500, so I don't want to visually overstimulate. So that's why I just cut it off at 7. I have, so the numerics gives us as many as we allow for one dimension. In fact, it's obviously the same, right? And just to not crowd the plot, I stop at 7. Yeah. Okay, yes, so there's a product state again for delta minus infinity. Okay, this is all well known. So now let's understand where the phase transition happens, the infinite order phase transition at delta minus 1. So I would like to draw your attention to the phase between -1 and +1. You cannot find the orange line for the second entanglement energy because it's hidden behind the green one. There's the degeneracy, and the degeneracy of the second and third entanglement energy is only lifted when they meet with a fourth and there's a crossing, and the degeneracy in the second and third is gone. And this lift of degeneracy marks the phase transition. The same is, by the way, the same is true for the degeneracy of 5 and 6 meeting with 7. Hence, by the way, hence why I cut it off at 7. And not 8, because it's another marker. Okay.
One question. So for
Yes.
if you think about symmetry protected topological phases, there are like degeneracies in the entanglement spectrum, which are like due to symmetry reasons.
Yes.
Right? So in your case, like how would you explain this degeneracies and the lifting of the degeneracies?
Yes, that's a very good question. I think there's not an obvious answer to that. So at -1, there is a yeah. So we have an U1 symmetry in the XY phase, which is not fully restored at -1. So I'm not sure that the degeneracy here represents a topological object, because again the degeneracy from Lee-Held and Haldane, the degeneracy needs to be apparent in all of the entanglement energies, right? So all of them are degenerate, and the entire spectrum is degenerate, which means that there are these two ground states. For example, I mean, in that case, it was two edge states. Yeah. So, and here we only find a degeneracy for a few, not all of them. Okay. The next thing that I would like to mention is that there seems to be something going on at something delta -1.5, where the first and second entanglement energy come very close. However, we think this is not a physical, like this is an artifact of finite size systems, which will not survive the infinite volume limit. We know this because we tested it. So we can move this, we can shrink this region towards delta -1 for larger and larger systems. So this system size is 200. And also other works have reported a very slow finite size scaling of the entanglement entropy towards -1. So this is we regard this as a finite size effect. So again, very uninteresting for us. Interesting for us is the degeneracy lift of entanglement energy 2 and 3. Okay, so now we've discussed this. We now know that this marks the phase transitions. Let's check it out for another alpha, for another values of alpha. For longer ranged and longer ranged alphas, we can see a movement of the phase transition to smaller and smaller delta, similar to what we just seen in geometric entanglement. And we can continue this and of course draw this marker of the phase transition in the delta alpha plane. which gives us this plot. Okay, here you can see, again, in red, the maxima of the geometric entanglement, and in blue diamonds, this level crossing, this change of degeneracy. And they almost perfectly overlap with each other, which is nice. So we kind of said, okay, both signal the same thing. They're entirely independent. Okay, this is nice. However, at the same time, if you paid close attention, and now I would like to show you the same animation a little bit faster, the entanglement spectrum for the long range case looks rather similar to the short range case. There's a kind of motion towards the left, starting at +1, and we're taking the short range entanglement spectrum and stretching it out to more negative delta, right? There's a stretching motion. None of these entanglement lines lose their height, quote unquote. None of them lose their entanglement energy. They just are shifted towards the left. And indeed, we can find a map of this value of delta to a new value that we're going to call delta tilde, which entirely reverts this motion, right? This motion towards the left. If this exists, we can squish it back in together and make the whole entanglement spectrum overlap with itself. So there's a self-similarity. And here in subplot A, I've shown it for values of alpha that have 1 over alpha that are smaller than 0.3, where the entanglement spectrum perfectly overlaps with itself of the short range case. So here again at -1, delta tilde or -1, the phase transition is signaled in the lift of degeneracy, and we can rescale this not only this feature of the entanglement spectrum where the degeneracy is lifted, but also the entire line over the whole values of delta that we inspected. And this is how the rescaling looks. It has a fixed point at +1, which means that +1 is not altered. And yes, in subplot B, you can see the entanglement spectrum rescaled for values of alpha that are larger than 0.3. And here you can see, okay, this works rather well for deltas that are close, delta tilde that are closer to -1, but it not so much works well for larger delta tilde. And perhaps you might even, it's fair to say that, okay, this breaks down. Yeah. Which gives us a motivation to study a phase transition that is perhaps happening here, right? So we see this rescaling works perfectly well for smaller delta, and it works, something seems to break down for values of 1 over alpha that are larger than 0.3. So this suggests a transition away from the phase of the short range XY phase, right? Because again, the entanglement spectrum is identical to the short range case up to a certain delta and certain alphas. So let's study the transition away from this. So for this, we're going to use renormalization group theory. And at the end of it, and this I want to say it, so now we are going to embark for a little intermezzo. At the end of it, I want to show you that we can combine these two things. We can combine renormalization group flow and the self-similarity to very precisely locate the phase transition into a different phase. And this is only going to be possible because we're going to combine them, and neither of the results on its own would have been able to locate the phase transition. But before we can talk about renormalization group flow, I need to introduce you to a field theory that we are going to be using to study renormalization group flow. And this field theory is called a Luttinger liquid in the short range XXZ model. It's valid over the whole gapless phase of the XXZ model. And this Luttinger liquid is a massless or gapless, a quadratic or free, conformally invariant, so with the conformal charge 1 field theory. It has two free parameters. It has an energy scale U and a dimensionless parameter K, typically called a Luttinger parameter, which is nothing but the compactification radius, if you're familiar with conformal field theory. Okay, so in the following, I would like to briefly talk about, like very quickly, say what a Luttinger liquid is, how we construct it, to be able to discuss the quantities that we are measuring in this theory. Don't take it too serious if you've never heard of it. I have some equations here, but it's more about the flavor of what we're going to relate to what, and how the picture falls into pieces. So the context again is we have a lattice model, and we're going to describe the low energy physics of this. We're approximating only the low energy physics by a bosonic field theory. So for that to be meaningful, we need to define a dictionary that relates, in our case, the microscopic spin degrees of freedom to bosonic fields. And we're going to do this, as always, like as almost everything in field theory, perturbatively. Perturbatively around the Gaussian fixed point at delta is equal to 0 and 1 over alpha is equal to 0. That means short range interaction. Okay, so we're going to start, as always, by, not as always, but now, as relating spins with fermions using Jordan-Wigner transformation. We're taking the free Hamiltonian, mapping it to free fermions. Then we're going to take these fermion modes around the point where the dispersion relation is 0. That means 0 energy, the low energy physics again. And take these modes to build up, to linearize this dispersion relation and build up field modes. Yeah, we're going to take these modes to make a fermionic field. This fermionic field is then translated into bosonic field with a bosonization formula. And at the end of it, we have a bosonic Hamiltonian where there's this field phi. Its momentum conjugate is theta, the derivative of this field theta. And this forms the identical Hamiltonian as this one within our approximations of this chain of reasoning. Okay, so now this is textbook, this is easy, quote unquote. What we next need to translate are the interaction terms, right? Because we want to study renormalization, which means that we need to include interaction terms and see when these interaction terms become relevant and irrelevant in renormalization lingo. For that, we need to employ our bosonization dictionary. And we're going to map the short range interaction of ZZ spins to a quadratic term in the field and a cosine interaction term. Okay, so this part here is going to be part of our quadratic Hamiltonian. This one is a real interaction term, real quote unquote, in terms of like it's not quadratic in field, and it's going to get its own coupling that we then renormalize. Next, we're going to translate the ZZ long range interaction into two gradients, right? So these are two gradients. However, this has been already studied before us many times, that this object is not relevant in our case. Relevant, it's only relevant if alpha is smaller than 1 or 1 over alpha is larger than 1, which means there is not like the real thermodynamic limit is debatable. But the next interesting term that we're going to introduce is the long-range interaction between S plus S minus, which gives rise to the cosine of the difference of the field theta. Okay. And again, over the long-range interaction potential. Okay, so these two couplings, these two interaction terms are going to be included in top of our field of our Gaussian fixed point. And let's see when we break away from this Gaussian fixed point. These are the first order perturbative flow equations of these two couplings. They become relevant if we set this coefficients to 0, and then we obtain a critical value of k, right? Because now everything is in terms of these 2 degrees of freedom in our field theory, k and u. U doesn't play a role because it's just defining the energy scale. K is our variable here at play. The critical K for the antiferromagnetic Luttinger liquid transition is given by K is equal to 1/2. Okay, this is well known. This has been textbook knowledge. Furthermore, the beta ansatz allows a relation between K and delta, which goes beyond perturbation theory. And this is a result that is non-perturbative, which you couldn't find just by employing Luttinger liquid theory or boson or just the bosonization. Okay. However, as you can see, the critical value for delta in the short range case can be quickly computed to be -1, right? So if you plug in -1 here in the Arcos cosine, we indeed get k is equal to 1/2, which is the critical k for this transition. Okay. However, we just seen that rescaling works for this transition, which made us believe we can take this analytic result and rescale it for this one value, for this one critical value of delta C to the long range case, right? So this here is an equation which is true empirically. We've seen it for this one value of delta. Now we're going to assume that this is true for all values of delta. We can rescale this curve to the long range case by taking the exact motion that we've just seen in the entanglement spectrum and stretching it out. So we take this result, stretch it out, this analytical result, and assume that this is true. So next, which is, by the way, which is something I can show you later, is actually holding up numerically. Yeah? So next we're going to study the other phase transition, the long range quote unquote phase transition, which is given by a critical line. If we set this equal to 0, it defines a critical K that is equal to 1/2 times 3 minus alpha. And now again, as I just said, we're assuming that K is not only equal to this, to the critical line that we just discovered from renormalization, but it's also equal to the rescaling of the analytical curve. Now this allows us here to draw a line in the delta alpha plane. When we employ this exact rescaling that we've just discovered, this is an alpha delta relation which we can solve for, and this allows us to draw this line here. Now this is nice. So first of all, I want to mention that this yellow curve is the rescaling of delta is equal to -1 onto the long range case. So we're stretching this out. The point where delta is equal to -1, and this is the curve that we find. Of course, this is really well matching with our phase transition that we found numerically by these other two observables. But furthermore, we can take the entire beta ansatz result, stretch it out, taking values of this other critical K, and find the phase transition towards a phase that is not anymore the Luttinger liquid. It's not anymore described by the short range XY model, but by a conformal continuous symmetry breaking case. And again, as you can see, the geometric entanglement does not signal as phase transition. It's only hinted in the entanglement spectrum in the form of this rescaling. And now we would like to back this up with numerical data. And for that, I need to introduce you two observables, which actually measure K, because now we're going to measure K to find a phase in this phase diagram that is truly Luttinger liquid, undoubtedly. For that, we're going to observe twice K, 2 times with 2 independent observables. And these two observables are, on the one hand, the Rayleigh entropy, which is equal to 1 over 1 minus, in our case, we call it n, the real parameter n, times the logarithm of the trace of the nth power of the reduced density matrix. Okay, in a finite size system, in the XXZ model, this object has oscillations with respect to the CFT formula. So the CFT formula in finite size systems is not realized accurately, but there are these oscillations. So this is, first of all, this is the CFT formula. It's the central charge over 12 times 1 plus 1 over n times the logarithm of a chord, the distance. So this object here defines the chord distance. I will show it to you in just a second. Secondly, there are these oscillations in the subsystem size. So you take the subsystem A, it's from size 0 to L, to minor L, and it's going to oscillate in the in this L. And the amplitude of oscillation is related to K. Okay, and these are the details. So the chord distance in an open boundary condition is given by this function, and the amplitude is given by this function. Next, the other observable that we're going to study is the correlation function. It's also well known that in conformal field theories, the correlation function falls off with some power of this parameter K. And then we're going to study this over the whole phase diagram. So let's first, let me first draw your attention here to the right-hand side. Here are different, here's again the phase diagram with different stars, different colored stars. I represent a point in this phase diagram. And we're going to study here in the same color coding, the two observables, fit our just seen functions, and extract a K. Okay, for example, here you can see the Rayleigh entropy with Rayleigh order 2 over the chord distance, the logarithm of the chord distance. And here you can see really well there's an oscillation, and in the infinite volume limit, you can sort of see that they approach each other, and there is the CFT result is true in the infinite volume limit. However, before that, we have this oscillation for different points in our phase diagram, which give different values for K. Similarly, we can look at the fall off of the 2-point correlation function, which gives us the another value for K. And we're going to ask two questions. First, is this fit to the Rayleigh entropy good? Is it consistent for different values of n? Because the formula, the amplitude here is independent. The formula that relates it to K is independent of n. Well, K is independent of n. Okay. Secondly, does the inferred K from this fit match this fit? And if both answers are positive, we say that this is within the Luttinger liquid phase. And indeed, if we perform this, we find the following boundary here marked in these purple triangles. So indeed, we can back up our claim from renormalization group study together with a rescaling that indeed, okay, we find the phase transition is indeed backed up by numerical data. Okay, and here, the last but not least, just for completeness, these are different plots for K. So I know this seems a bit messy, but let's first say, look at subplot A here. you see K over delta for different values of alpha, color-coded up to 0.3. And in subplot C, you see the same thing rescaled to delta tilde. And you can see that this perfectly matches the short-range result. The different symbols here, stars and dots, represent the two different measures of, on the one hand, Rayleigh entropies, and the other correlation functions. And indeed, you can see outside this phase diagram, outside this of delta tilde, smaller than -1, the two disagree, which is also another sign that we don't have Luttinger liquid theory. We don't have a Luttinger liquid anymore. And here the same is true for values, for larger values of alpha. Perhaps this is even more impressive, that these points rescale perfectly onto the short range result. Again, this rescaling is only taken from the entanglement spectrum result. It's not a different rescaling. They're not different parameters. These are the same parameters. Okay. So with this, I want to finish, and my takeaway message would be that we studied this phase diagram with geometric entanglement and the entanglement spectrum. We studied the renormalization group flow, and either of these would have not been sufficient enough to draw this teal line here and to find these purple points. But only in combination of this analytic result in the short range case, stretching it out to the long range case, we can find this teal turquoise line in the phase diagram. And secondly, well, last but not least, I would like to mention this other work that we've done, in fact, together with Stephen, which has come out last year, if you're interested in that. Okay, now please ask questions. Well, now I'm looking at you, so you have this black dot here in the corner.
Yeah.
All right, well, thank you very much, Jan. Yeah, okay. I was going to open the floor for questions, but Shozab, you've jumped right in. Go for it.
No, okay, thanks. So great talk, Jan. Thanks so much. So I guess to start off with, could you give some more condensed matter intuition as to why the geometric entanglement is a good measure to look at? And for which systems do you expect it to be a good measure?
So the geometric entanglement works in our case. So well, let me show you the Hamiltonian. In fact, let's jump here. The geometric entanglement works in our case in this system really well, because for values of delta that are between -1 and 1, you might assume, okay, like your mean field guess for the ground state is any state that is polarized, like a product state that is polarized in the XY plane. And for a value of delta that is smaller than -1, you might say, okay, this is antiferromagnetic, there's a frustration, so let's take, like, our mean field guess is the antiferromagnet, right? So a Néel antiferromagnet, completely alternating spin up, spin down. And these are the two guesses for a mean field ground state. And these two, in the geometric entanglement works so well because it, oh no, now I went too far, because it follows these two states. So these two product states, the overlap is exactly maximum here at -1. So these two states have the same overlap with the ground state, and then it switches, like it suddenly switches. The closest product state is not anymore so if you come from the XY phase, it's not anymore in the XY plane, but it's this Néel antiferromagnet.
But could one make the point here? Sorry to follow up on this question. that's
Yeah.
basically like amplifying the signal. I mean, we found something similar when we looked at the many-body localization transition, where we looked at that what we call the diagonal ensemble, but that's something quite related to the geometric measure of entanglement, where we looked at like overlaps with products, and where, I mean, the identification of the phase diagram was just easier because there was a system size dependence coming in, because you look at the n-fold product of something compared to just entanglement entropies of subsystems. So is this maybe a point that the signal strength is better and amplified through this geometric measure, or is this a bogus point?
No, I think you might be right. Yes, I think you're right here. Yeah, no. So the overlap is, of course, scales with the system size, and is really amplified by the system size. Yeah, yeah.
I had another question. Perhaps I think I might have missed some subtlety in your talk, but is there any kind of CFT daughter that can be extracted from the geometric entanglement?
Sorry, is CFT?
Is there some CFT daughter that can be extracted from the geometric entanglement?
A daughter? I'm not familiar with that vocabulary. I'm sorry.
Data. Sorry.
Data. How do you mean? So yes, we measure,
for instance, like central charges or conformal scaling dimensions.
Yes. So our our fit here measures the central charge. Yeah. So we leave this open. We can find a central charge. So this is something that I haven't mentioned explicitly, but a third question here. So again, we perform these fits everywhere in this phase diagram. A third question that we can ask is C almost 1? Like, how close is it to 1? And it perfectly agrees with this phase boundary.
Well, you're finding the central charge from the Renyi entropies, right?
Yes.
Yes. Yeah. I guess what Sozep asks is if you could do something similar from the geometric entanglement.
From the geometric entanglement, I don't know. I'm not aware of a procedure how this works out. I don't know. No, I don't know. I'm sorry.
Yeah. No worries.
Well, but maybe you can get the central charge from the scaling of the entanglement entropy of a block of size L. So if you take your finite MPS and you do a block of L sides and you scale this L up and you compute the entanglement entropy, then you can find probably the central charge as well. So there are also formulas for that.
Yes. Yes. So this here again, this formula is the one in the XXZ model, and you can of course take this. So it leaves this as a parameter free. Take a fixed n, take a fixed system size, and vary the block. And then you, from a fit, like, okay, you can, in varying L, you can measure the central charge as well. Yeah. In fact, this is how we did it. Yeah. We didn't vary n. We varied the block size. Yeah. Because it's also the signal of the amplitude here. Yeah. And this looks like this then, right? So, and the asymptotic line here has a slope, and the slope is given by the central charge.
So maybe I missed this, but what is the nature of the phase transition towards the symmetry broken phase?
Yes, very good question. I'm not sure. To be completely fair, I'm not sure, because so this is a subtlety that I would love to be enlightened about, because again, what is renormalization group theory? It's a tool to study second order phase transitions. So how can we find an infinite order phase transition with the tool that is designed to study second order phase transitions? The answer is the field theory that we're constructing simply breaks down at the point where our microscopic model undergoes an infinite order phase transition. But the field theory that we construct around it undergoes a second order phase transition. So these two coincide, and there's a signal that, okay, something here is fundamentally changing in the field theory. And ultimately, only with the beta ansatz, we know, okay, this is not a coincidence, like this is not an approximation that's going wrong. This is really fundamentally in the model, in the microscopic model. And this is only an input from the beta ansatz, from an analytic result, right? This object here, for example, can be seen as something like this. This here tells you that indeed there is a relation. There's a coincidence. Like there's not just a coincidence. It's a one-to-one map. Yeah.
May I ask a question? Well,
Yes.
How do you know that field theoretic approximation will have a second order phase transition?
Sorry, I didn't get the beginning of your.
How do you know a priori that the field theory that you write down for this microscopic model will have a second order transition?
So this is the logic that that renormalization group theory follows. That perhaps.
So you're saying you write the field theory and RG works, so it must have a second order.
Yes. So we write the field theory. Do I have the? Yes. So here we write the field theory. We include these interactions, and then. By definition, we will find second order phase transitions in our renormalization group flow. And in fact, you can sort of relate to this, that it's one slide before, that the field Hamiltonian here, this Gaussian fixed point, undergoes to a first order phase transition. So our first order phase transition between the XY phase and the ferromagnetic phase is given at delta +1. And at delta +1, the Arcos cosine is 0, which means that the K goes to infinity. And this is something that can never happen in our field theory, right? So if you draw a phase diagram in the field theory variables, you would have to go to infinite K to undergo this phase transition, which of course means, okay, the field theory is not valid. And in some sense, you can say there's no finite K such that we can cross this phase transition.
I see. And all the higher order transitions, they're thrown away in the irrelevant parts, or?
Yes. So this here is a first order flow equation. It's rather interesting that this suffices to characterize the phase diagram. They're not coupled,
right?
And everything higher is not necessary turns out to be not necessary. There have been previous studies which have studied this with higher order terms. So second order is rather intricate. It's also, I think it's mathematically questionable how to obtain the amplitudes, the field amplitudes with a long range interaction terms. It's very intricate. It's very subtle. So my point here really is that this is simple, and this is sufficient if you combine it with rescaling. The rescaling that we found allows it to take this K, to take the function, the analytic function of K, of delta, to the long range case. And this allows us to draw the phase diagram. And it's not possible without taking the rescaling into account.
I see. Okay. Cool. Thanks.
I've got another question. So typically, the phase transition is accompanied by a divergent correlation length. And since you have access to entanglement spectra, it would be very easy to compute the correlation length from the subdominant eigenvalue of the transfer matrix. I mean, you have access to the transfer matrix, basically. I don't know if this works in the finite setting as well, but if you can compute the correlation length, you can also do an infinite bond dimension scaling by taking different gaps in the spectrum of the eigenvalue of the transfer matrix, and then see how the correlation length behaves for different delta and alpha. And do you maybe have a feeling if this would give you access to the transition that you don't find by the geometric entanglement, for instance?
I'm not sure. I tried to look at signals in the entanglement spectrum for this continuous symmetry breaking phase transition. But I have a counter question. I'm sorry. I'm going to counter your question. Can we exercise what you just said for
maybe it doesn't even make
the
sense in
antiferromagnetic phase transition?
Maybe it doesn't even make sense in the finite setting because, well, you don't have a transfer matrix in the strict sense because it's not translational invariant anymore. So maybe the question doesn't make too much sense.
Might be, yes. I'm not familiar with the technique. I haven't worked with it, so I'm not entirely confident. But how does it work for the antiferromagnetic case? So for the phase transition in the short range case, does this work? I mean, I'm just going to post a question back. Sorry, because I don't have an answer for you.
I mean, for sure, if you have an infinite system and you have a transfer matrix, so like, let's say you have a translational invariant MPS and you have the transfer matrix for this object, you can compute the eigenvalue spectrum of this. And from this eigenvalue spectrum, you can compute the correlation length, and also using like the second or the third gap in the spectrum, you can do infinite bond dimension extrapolations. So if you increase the bond dimension to infinity, how would your correlation length behave? And this is a signal that you can use to identify phase transitions, because near the critical points, your correlation length will diverge.
So it's just to be sure, it's this correlation function that has a scale like this, right? So it has some it scales a difference.
Well, it's a dominant correlation function, so I guess it's something like spin-spin correlation. Yes.
Yeah. So in the CFT case, this is because we're still technically on the boundary. We can describe it with this CFT of k is equal to 1/2. And then we have this correlation length. So it's analytically known. I mean, the spin-spin correlation function, as well as any, oh, sorry, now I'm lost, as any correlation function in these field modes. They are just trivial, like quote unquote trivial to be computed. So I'm not sure that there's actually anything divergent, because it still renormalizes to this Gaussian fixed point, to this free theory. So that's like part of the nature of this infinite order phase transition. That's just no signal in the correlation function. So my intuition would be that you won't find anything. Like the phase transition is not signaled in this scaling. And I think it's this now extrapolating, and I think it's also true for the other one, for the continuous symmetry breaking phase transition.
I see. Yeah, maybe also the question wasn't so meaningful in the first place because it's a finite system. Yeah. Okay, thanks.
Oof, yeah.
Yeah, can I ask a very nitty-gritty question? Actually, not on the physics, but rather on the numerics. Sorry, I should have asked this question earlier, but somehow I didn't get to. So
no worries.
The question is basically how stable the computation of the geometric measure of entanglement actually is, and whether you encounter instabilities or issues here somehow. And the background is that, I mean, sometimes you have this intensive network theory that if the underlying problem is like computationally hard or undecidable, even, that you get numerical instabilities of some type. Like, for example, like to test the positivity of an MPO is not only hard but undecidable, which means that you have the tensors of a matrix product operator, and you just ask, are all incarnations or all instances of that operator that you get out for all lengths positive semi-definite, and could hence represent valid quantum states. And it turns out that this question is not only hard, but in fact undecidable, where I give you the input of the tensor, and you will not be able to decide for all lengths whether this is a positive operator or not. Why am I saying this? Because that's a theorem, but people have been complaining about numerics. Like, I don't know, Ari-Carmen Banul was complaining when she did like open systems research with Lindbladians and so on, that she had problems to get the numeric stable, and she had like small negative eigenvalues and of the presumed density operators, and it was kind of hard to get under control. And this is kind of like a mirror of the hardness of the underlying problem that is mirrored in the numerics, that you can't really keep it under control. Now, if you have a many-body state and want to compute the best overlap, even with a single product, like big state, and you ask what's the best overlap with a product like psi A and psi B, even that is a hard problem. It's actually hard, yeah, in worst case complexity, which you can show as it's a cute argument. You can use this problem as an oracle in like slicing algorithms that would solve the separability problem in polytime, which is an NP-hard problem. Never mind. So in a way, the problem of computing the geometric of entanglement, measure of entanglement, is basically an NP-hard problem, properly stated as a decision problem. So is there any signature of that you see in your numerics, that it's tricky, or is that just not appearing because you have small dimensions and they're just not the hard instances? So that was a bit of a vague question, but
yeah.
If I may just say something, a similar thought occurred to me during the talk. The thing that caught my eye was the entanglement entropies when they're overlapping. You know, when you slide to the right. No. When you have in your animation.
Here, yes.
Yeah. So that was one thing that caught my eye. Like, is it possible to know whether the entanglement entropies will overlap at some later delta?
I think I don't. I think so. First of all, this is an unrelated question to Jens' question. If I'm
well, it's more a bit related, but maybe it's a bit too far off. But my basic question is very simple, namely,
yes. So
is it
let
stable?
me come to
Do you
let me
encounter
answer
instabilities?
Yes. So let me first answer this one. The basic answer is no, because the approach that Stephen and I took in measuring this object of the geometric measure of entanglement is taking the state that we've given, like the ground state, and truncating it to a single value, which is
then you don't get a problem.
Turns out to be a really good ansatz for this quantity, because now we can say,
indeed, I completely buy this. I mean, I also know that this can't be the universally optimal answer, because otherwise it would really strictly contradict what I said before. But I do buy that in practical settings, this is what you should do. You basically just, you just basically truncate to the leading product form.
Yes.
From the ansatz. Yeah, that makes sense. No, I as a pragmatic attitude, I buy it. It's still an interesting.
No, we haven't found. In fact, I can say that for large systems, the optimization sweep. So now we have this given ansatz. We optimize it with respect to the overlap, and there are almost no sweeps. They're 1, 2 sweeps from left to right or right to left, and then our algorithm converged. So in fact, the simple truncation already is an almost optimal result within this starting point. So
yeah, I buy it.
Instability is really not apparent.
Sorry, that was a bit of a too long question, but
no, of course.
It's worth also just mentioning, just attached to that when we came up with this and started trying to use it, one of the biggest challenges was finding something to benchmark it against, because the geometric entanglement was so much easier to compute and more accurate than other more standard measures. So looking at things like the magnetic susceptibility, for example, Jan spent a lot of time working on that, and it was very, very difficult to show that it agreed with the geometric entanglement. The geometric entanglement was just so much easier to compute.
Yes. So again, this goes back to the statement that there are different magnetic properties of these three different phases. And this one is paramagnetic and this one's antiferromagnetic. Now you might say, okay, this is obvious to measure. Turns out it's not. The onset of these two features is continuous. It's perfectly continuous, perfectly smooth. So to measure this phase transition is, again, infinite order. It's not going to happen in this susceptibility. Okay, coming back to the other question about the may I ask for reposing the question about these entropies here?
Sorry. So as you go through this animation, these entanglement entropies are coming closer to each other.
I think that was Rosap's question, no?
Yeah.
Yes.
Is it possible to determine whether or not they will intersect?
I think in the limit of alpha to 0, they must all be the same. Yeah, it must be a I think they all approach each other.
Oh, so that's guaranteed.
There's an all-to-all connection. All of them are equal. There's no spatial preference in this bipartition, which for some symmetry reasons I would assume makes the system that we have into a graph, right? Into this an all-to-all graph. And then the bipartition means, okay, they must be all equally weight in the limit of delta alpha to 0. And then I would assume, that's why I would assume they approach each other for the largest values of here of alpha. Yeah.
I see. Okay.
Did that make sense? I hope it makes sense. At least.
Sense.
I have a question about. I have one more question about the BKT transition.
Yes.
So I'm a bit confused because I was expecting that for delta is equal to 1, of course, this is a singular point, as you said, K diverges and so on. But for delta larger than 1, the XXZ model is gapped, and it can be described by the Sine-Gordon model. Is that right?
Yes. So this is exactly what you see here. That for this spin-spin interaction is translated into, okay, the quadratic part plus this Sine-Gordon potential.
Right. And this change is reflected in the correlation functions from algebraic power law correlation functions. You get into exponentially decaying correlation functions.
Yes, very much so. And it's acquired. It's associated to a finite value for the field. Right. So a mass is acquired. In field theory terms, there's something like a mass.
So shouldn't you see this also in the case of alpha different from 0? From away from the XXZ point.
Yes,
XXZ
yes.
line.
So this is in very much, so these here are rather similar, right? They are both sort of a Sine-Gordon potential.
But for different...
but for different values in space, okay. However, this means that there's again a mass acquired in this field theta, which means there's the field theta corresponds to, so if you take classical view on this, it corresponds to the angle inside the XY plane. And now if you acquire a finite value for this, you lose the U1 symmetry and you get a fixed finite value. And this represents the symmetry breaking, the continuous symmetry breaking. And it's very much something like the transition to the to the other phase of the St. Gordon model. Yeah. So again, correlation functions do not decay anymore with the power law. Yeah.
Okay, so this can be used to observe the transition then.
Yes, so these two operators are driving the transition away from this conformal field theory point.
Okay.
Yeah,
Thank you.
yeah.
Okay, so any final questions? We've had quite a lot so far. That's been really nice to see. No, that's everything. Okay, well, in that case, I think we thank Jan again for that really nice talk and for the very interesting discussion that followed. Thank you.
Thanks, guys. Thanks, guys, for listening. Thanks so much.
Thanks. That's wonderful.
All right. Take care. Bye-bye.